Black holes are the most extreme objects in the universe. They crush stars, bend light, and slow time to a near standstill. But hidden inside their darkness is a question that refuses to go away. Could these cosmic monsters do more than trap matter? Could they twist time itself so violently that they open a door to the past? Physics does not laugh at this question. In fact, when we follow Einstein's equations to their limits, they lead us uncomfortably close to the idea that black holes might be nature's most dangerous time machines. When we talk about black holes, we are not talking about ordinary objects in space. We are talking about places where the universe pushes its own laws to the brink of collapse. At the edge of a black hole, gravity becomes so intense that it does something extraordinary to time itself. Time, which we usually think of as steady and universal, begins to slow down. This is not philosophy or speculation. It is a direct and unavoidable consequence of Einstein's theory of general relativity. As gravity increases, time stretches. Near a black hole, this stretching becomes extreme. To an observer far away, watching from a safe distance, a clock falling toward a black hole appears to tick slower and slower. Each second takes longer than the last. As the clock approaches the event horizon, time seems to nearly freeze. This effect is so dramatic that, from the outside, nothing ever truly crosses the event horizon. A falling astronaut would appear suspended there forever, frozen in a final moment. Light emitted from their body becomes redder and dimmer, stretched to longer wavelengths until it fades away entirely. The universe does not see them disappear, it sees them slow into silence. This strange behavior tells us something profound. Time is not absolute. It bends, stretches, and distorts under gravity. And black holes are the most powerful time-warping machines ever discovered. What makes this even more astonishing is that this freezing of time is not felt by the falling traveler. From their perspective, their own clock ticks normally. Their heartbeat remains steady. Seconds feel like seconds. They do not experience time slowing down at all. This split reality, where time behaves differently for different observers, is one of the deepest lessons of modern physics. It means that time is personal, shaped by motion and gravity. Near a black hole, two versions of time coexist, each equally real. This leads to an unsettling realization. If time can slow to a near halt at the edge of a black hole, then black holes already possess the essential ingredient required for time travel. They do not need science fiction machinery or exotic technology. Nature itself has built these cosmic devices. By approaching the event horizon, one can manipulate time far more dramatically than anything possible on Earth. Satellites already experience tiny versions of this effect due to Earth's gravity, and we must correct for it in GPS systems. A black hole simply amplifies the same principle to an extreme. This extreme slowing of time raises a natural question. If time can nearly stop, could it reverse? Physics does not say yes, but it also does not dismiss the question outright. Instead, it shows us the limits. The equations allow time to stretch arbitrarily, but they resist allowing it to flow backward. At the edge of a black hole, time is strained, not broken. The universe permits enormous distortion, but it stops just short of contradiction. This is a recurring theme in physics. Nature allows complexity and drama, but it preserves consistency. Now consider what happens if you do not hover near the event horizon, but instead fall straight toward it. As you approach the black hole, you are not going back in time. Quite the opposite. You are racing forward into the future. While only minutes or hours pass for you, years, centuries, or even millions of years may pass for the outside universe. You emerge, if that word can even be used, into a far future version of the cosmos. In this sense, black holes are not gateways to the past, but express elevators to the future. This effect is not limited to black holes. Any object moving close to the speed of light or sitting in an intense gravitational field experiences time dilation. But black holes push this effect to its ultimate limit. They allow the greatest separation between personal time and cosmic time. A traveler skimming close to the event horizon could in principle witness the end of civilizations, the death of stars, and the slow transformation of galaxies, while experiencing only a short journey themselves. This is time travel that physics fully endorses because it does not violate cause and effect. What makes this one-way time travel acceptable is that it respects causality. Causes still come before effects. Information still flows forward. Nothing is undone. The universe seems perfectly comfortable allowing us to move into the future faster than normal. It does this naturally, every moment, everywhere. Black holes simply exaggerate the process. They do not create paradoxes, they create separation. This asymmetry is crucial. The laws of physics are surprisingly tolerant of time dilation, but deeply suspicious of time reversal. When you fall toward a black hole, entropy still increases. Information still evolves. Memory still accumulates. You are not erasing events, you are skipping ahead. This is why black holes, despite their terrifying reputation, remain lawful citizens of the universe. They obey the rules even when they appear to break our intuition, yet this very obedience hints at a deeper truth. If black holes can take us so dramatically into the future, why can they not send us into the past? The answer seems to lie in how the universe treats information and stability. Moving forward in time is stable. Small changes do not explode into contradictions. Moving backward, however, threatens to unravel everything. Near a black hole, the closer you get to conditions that might allow backward motion, the more violently the universe responds. The future-facing nature of black hole time travel suggests that time itself has a preferred direction, an arrow enforced not by philosophy, but by physics. Gravity bends time, but it does not flip it. Even in the most extreme environments known, the universe chooses progression over revision. The past remains fixed, locked into the structure of space-time, while the future stays flexible and open. Black holes, then, do not tempt us with forbidden access to yesterday. Instead, they confront us with the reality of tomorrow. They show us that time is not a river flowing uniformly for everyone, but a dynamic landscape shaped by mass and motion. They demonstrate that the universe is far stranger than our everyday experience suggests, yet far more disciplined than our fantasies imagine. And in that tension between possibility and restraint, black holes reveal not just how time can be bent, but why it refuses to be broken. Once the event horizon is crossed, the universe reveals a side of reality that feels almost hostile to common sense. Outside a black hole, space and time behave as we expect. You can choose where to go in space, but time relentlessly moves forward. Inside, this balance collapses. According to the mathematics of general relativity, space and time exchange rules. What was once a direction in space becomes a direction in time. The singularity is no longer a place you might steer around. It becomes a moment that lies inevitably in your future. Just as you cannot choose to stop aging or step sideways out of tomorrow, you cannot avoid the singularity once you pass the event horizon. It is as unavoidable as the next second. This role reversal is not poetic metaphor, it is encoded directly into the equation. Inside the black hole, moving forward means moving closer to the singularity, just as moving forward in time means aging. There is no known force, no rocket, no technology that can halt this progression. Even light itself cannot escape this fate. This strange structure tells us something crucial about time travel. If time is no longer something you can turn around or navigate freely, then the very idea of choosing a path back to the past begins to collapse. The geometry of space-time itself forbids it. Yet this does not stop physicists from pushing the equations further, asking what happens in more complex black holes. When rotation is added, the story becomes far stranger. A rotating black hole drags space-time around with it, twisting the fabric of reality like a whirlpool. This effect, known as frame dragging, becomes so extreme near rapidly spinning. Black hole that space-time is pulled along faster than light itself could resist. In this warped region, the equations produce astonishing possibilities. In these solutions, paths appear that loop back on themselves in time. These are not science fiction inventions. They arise naturally from Einstein's equation. A particle following one of these paths could, on paper, return to an earlier moment in its own history. This is where the idea that black holes might allow travel into the past gains its strongest mathematical support. The equations do not immediately forbid it. They allow time to curve so tightly that it closes into a loop. For a moment, it seems as though physics has opened a forbidden door. If such paths exist, then causality, the idea that cause must precede effect, appears to be under threat. One could imagine information arriving before it was sent, or events influencing their own origins. This is where black holes stop being merely exotic objects and start challenging the logical foundations of reality itself. However, mathematics alone does not guarantee physical reality. The same equations that allow these time loops also hint at their instability. The closer one gets to these regions, the more violent the environment becomes. Tidal force grow without mercy. Energy densities spike. Even tiny disturbances can amplify catastrophically. The universe seems to resist the formation of stable time loops, as if they were cracks forming in the structure of existence. This resistance becomes clearer when quantum physics enters the picture. Near regions where time loops might form, quantum fluctuations do not remain small, they explode. Virtual particles, which normally flicker harmlessly in and out of existence, begin to accumulate energy. Radiation intensifies. The vacuum itself becomes unstable. Instead of a smooth passage through time, these regions collapse into chaos. The very mechanisms that would be needed to support backward time travel appear to self-destruct the moment they begin to form. This suggests something deeply important. The universe may allow the equations to hint at time travel, but it enforces a kind of cosmic censorship. Whenever a configuration threatens to violate causality, nature responds by destabilizing it. Black holes, especially rotating ones, act like laboratories where these principles are tested to their limits. Again and again, the result is the same. Extreme distortion is allowed, but paradox is not. What emerges from this is a subtle lesson about how seriously the universe treats consistency. Time loops are not forbidden by a simple rule, they are forbidden by instability. The laws of physics do not shout no, they quietly make backward time travel impossible to sustain. This is far more elegant and far more unsettling. It means the universe protects its own history not with walls, but with fragility. Any attempt to bend time into a loop causes reality itself to tear apart. This also reshapes how we think about black holes as potential gateways. They are not doors carefully locked to keep us out. They are more like bridges that collapse under their own weight the moment someone tries to walk across them in the wrong direction. The mathematics tempts us forward, but the physics pulls the ground away beneath our feet. In this sense, black holes teach us that time travel to the past is not banned by decree, it is defeated by consequence. The closer we approach conditions that might allow it, the more destructive those conditions become. Energy rises, structure dissolves, and predictability vanishes. The universe sacrifices smoothness to preserve order. And so, even in the most extreme environments imaginable where gravity reigns supreme and time itself loses its familiar meaning, a pattern holds. Time can stretch, slow, and twist. It can separate observers by eons. It can accelerate us into futures far beyond our natural lifespan. But when it comes to reversing direction, when it comes to rewriting what has already happened, the fabric of space-time stiffens and fights back. Black holes, especially rotating ones, stand at the edge of this cosmic boundary. They whisper that time travel to the past is mathematically imaginable, yet physically unattainable. They show us how close reality can come to paradox without ever crossing into it. In doing so, they reveal that the universe is not careless with time. It treats the past as something that must remain intact, even if everything else is allowed to bend. As we push deeper into the heart of a black hole, all roads lead inevitably toward the singularity. This is the point where our equations scream in protest, where density becomes infinite and the known laws of physics simply stop working. It is tempting to imagine the singularity as a gateway, a portal, or a hidden tunnel through space and time. But the reality suggested by modern physics is far less accommodating. The singularity is not an opening, it is a boundary. It marks the edge of our understanding and quite possibly the end of any physical process as we know it. Near the singularity, tidal forces become unimaginably violent. Even atoms cannot survive. Matter is stretched and compressed in different directions with such intensity that no known structure can remain intact. This alone makes the idea of passing through the singularity problematic, but the deeper issue is conceptual. At the singularity, time itself loses meaning. The equations no longer tell us what comes next. Without a functioning notion of time, the idea of traveling back to an earlier moment collapses. You cannot go back in time if time itself ceases to exist in any definable way. This is why many physicists view the singularity not as a doorway to other eras, but as a signal that a deeper theory is needed. General relativity, magnificent as it is, cannot describe what happens at this extreme. Something more fundamental must take over, and that something is expected to be quantum gravity. When quantum mechanics is combined with gravity, the picture changes dramatically, and not in a way that favors time travel to the past. Quantum physics introduces uncertainty, fluctuation, and instability at the smallest scales. Near a black hole, these effects are amplified to cosmic proportions. Regions that appear smooth and continuous in classical physics become turbulent and unpredictable. Virtual particles pop in and out of existence with increasing energy. Radiation builds up. The closer one gets to conditions that might allow exotic structures like time, loops or tunnels through time, the more violently the quantum vacuum reacts. This reaction is not subtle. Calculations suggest that energy densities near these hypothetical time travel regions would grow without limit. Radiation would flood the area, destroy any structure that could support a stable path backward in time. In effect, quantum mechanics acts like a self-defense mechanism for the universe. It destabilizes any configuration that threatens to violate causality. Time travel to the past does not fail because it is forbidden by a signpost. It fails because the environment becomes catastrophically hostile. This pattern appears again and again whenever physicists seriously examine proposals for backward time travel. Wormholes collapse. Time loops disintegrate. Exotic matter required to stabilize them behaves in uncontrollable ways. The universe allows us to write down equations that flirt with paradox, but when we ask whether those equations describe something that can actually exist, the answer keeps returning as no. The structures tear themselves apart before they can be used. Black holes, then, are not loopholes in the laws of time. They are stress tests. They show us how far time can be bent without breaking. They reveal that causality is not a fragile rule easily overturned, but a deeply protected feature of reality. Even when gravity becomes overwhelming and space-time is twisted into extreme shapes, the universe preserves the sequence of cause and effect. This becomes even clearer when we consider information. Modern physics increasingly suggests that information is never destroyed. Even black holes, once thought to erase everything that falls into them, now appear to preserve information in highly scrambled forms. This has profound implications for time travel. If information about the past is encoded throughout the universe, then changing the past would require rewriting that information everywhere. The sheer scale of this task makes it effectively impossible. Information does not simply sit in one place. It spreads, entangles, and leaves imprints across space-time. Every interaction echoes forward. To go back and alter a past event would mean unraveling an enormous web of correlations that now define the present. Black holes, far from allowing this, seem to reinforce it. They scramble information but do not eliminate it. They preserve history even as they hide it behind an event horizon. What emerges from all this is a consistent theme. The universe is remarkably permissive when it comes to the future. It allows branching possibilities, quantum uncertainty, and open outcomes. But it is deeply conservative about the past. Once events occur, they become part of the fixed structure of reality. Black holes do not undermine this structure, they underline it. They show us that even in the most extreme environments imaginable, the past is not something that can be revisited or revised. Instead of offering a path backward, black holes force us to confront the limits of our theories. They tell us that time travel to the future is easy and natural, woven into the fabric of relativity. Time travel to the past, however, runs into barriers that are not merely technical but fundamental. Gravity resists it. Quantum mechanics destabilizes it. Information theory forbids its consequences. In this way, black holes act less like cosmic shortcuts and more like cosmic guardians. They guard the consistency of time by pushing any attempt to violate it into regimes of chaos and breakdown. They show us that the universe values coherence over convenience, stability over nostalgia, and the deeper we peer into their darkness, the clearer it becomes that the past is not hidden. There, waiting to be accessed, but protected there, sealed away by the deepest laws of nature. As our understanding of black holes has matured, one of the most surprising revelations has been the role of information. For decades, black holes were thought to be cosmic shredders, erasing everything that crossed the event horizon. Matter, energy, even the history of objects seemed to vanish forever. This idea was deeply troubling because it conflicted with a central principle of modern physics: information cannot be destroyed. When these two ideas collided, the result was not a loophole for time travel, but a deeper appreciation of how carefully the universe guards its past. Information is not abstract, it is physical. It is encoded in particles, fields, and quantum states. Every interaction leaves a trace. When something happens, that event is not isolated, it ripples outward, entangling itself with the rest of the universe. Black holes do not erase these ripples. Instead, they scramble them beyond recognition. Information that falls into a black hole becomes distributed across its surface, and radiation in ways that are staggeringly complex but not lost. The past is preserved, not deleted. This has enormous implications for time travel. To go back in time and change an event would require altering information that has already propagated throughout the universe. It would mean rewriting not just one moment, but every consequence that flowed from it. The universe does not allow such selective editing. Once information spreads, it becomes part of the cosmic record. Black holes, far from weakening this record, reinforce it by showing how. Even the most extreme environments respect information conservation. This leads to an unexpected conclusion. The more we understand black holes, the less freedom we have to tamper with history. They appear to be vaults, not doorways. They hide information, but they do not let it be undone. The past becomes encoded into the structure of space-time itself, protected by layers of physical law. Any attempt to revisit or revise it would require violating principles that are foundational to reality. At the same time, black holes teach us something liberating about the future. While the past is rigid, the future remains open. Quantum mechanics allows uncertainty. Probabilities unfold rather than certainties. Multiple outcomes remain possible until events occur. This asymmetry is not accidental, it is built into the laws of physics. Entropy increases. Information spreads. Time flows forward because the universe is evolving, not because it is replaying itself. This arrow of time becomes especially clear near black holes. Matter falls in, radiation leaks out, complexity increases. Even as black holes evaporate over unimaginable timescales, they do so in a way that preserves the logical structure of cause and effect. Nothing jumps backward. Nothing rewrites what has already been established. The universe allows change, but only in one direction. What black holes ultimately reveal is that time is not a simple dimension like space. You can move left or right, forward or backward in space, but time resists symmetry. It has a preferred orientation. Black holes stretch and distort it, but they do not reverse it. They amplify the arrow of time rather than bend it into a loop. In doing so, they expose a deep rule: reality evolves, it does not revise. This perspective reshapes how we think about time travel fantasies. The idea of going back to fix mistakes or observe ancient moments is emotionally compelling, but physics points us elsewhere. The universe is not designed to let us correct the past. It is designed to let us learn from it. Black holes, in all their violence and mystery, make this lesson unavoidable. They confront us with the cost of tampering with causality and show us that stability demands restraint. Rather than granting access to earlier eras, black holes force us to face the present and the future. They remind us that every moment is precious precisely because it cannot be repeated. Once an event happens, it becomes woven into the fabric of existence. No amount of gravity, no collapse of stars, no twisting of space-time can pull it back out. In this way, black holes are not enemies of time, they are its enforcers. They operate at the edge of physics, where theories strain an imagination source, yet they consistently point to the same conclusion. Time can be slowed, it can be stretched. It can separate observers by billions of years, but it does not forgive reversal. The deeper we explore black holes, the clearer it becomes that the universe is not hostile to curiosity, but it is deeply committed to coherence. It allows us to peer into its most extreme structures and ask forbidden questions, but it answers with consistency rather than contradiction. Black holes stand as monuments to this principle, demonstrating that even at the limits of reality, the past remains untouchable, while the future remains unwritten. When all of these ideas are brought together, a powerful picture of time emerges. Black holes, which once seemed like possible escape routes from the rules of reality, instead reveal how deeply those rules are protected. They show us that time is flexible but not fragile. It can be stretched, slowed, and distorted beyond anything we experience in everyday life. Yet, it refuses to fold back on itself in ways that would destroy causality and meaning. The universe permits us to move forward at different speeds, but it does not allow us to rewrite what has already been written. What physics ultimately teaches us is not disappointment, but clarity. The past is stable because it must be. Memory, identity, learning, and progress all depend on a fixed sequence of events. If the past were open to revision, reality would dissolve into contradiction. Black holes, at the very edge of known physics, reinforce this lesson more clearly than any other object in the cosmos. They push time to its limits and reveal where the boundaries truly lie. And in that realization, there is something strangely empowering. The future remains open, shaped by discovery, choice, and understanding. The universe does not invite us to escape our history, but it invites us to build upon it. Thank you for watching, and thank you for exploring the mysteries of time and black holes with us.